Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 21 on Substitution.
Now that we've seen what indefinite integrals are good for, differential equations and more, we turn to the problem of the mechanics of integration. How does one compute an antiderivative? That is a large and convoluted subject. In this lesson, we'll begin with our first method, that of substitution.
Our first set of strategies for computing integrals exploits the fact that integration is anti-differentiation. Therefore, integration rules can be derived from differentiation rules. Let's consider, for example, the linearity rule for derivatives. What this tells us when we take those rules and then integrate them is that integration is also linear. The integral of a sum is the sum of integrals. The integral of a constant times an integrand is that constant times the integral. So, integration, like differentiation, is a linear operator, as you certainly already knew. Other differentiation rules lead to other integration techniques. We're going to focus on the chain rule, where tradition dictates the use of u as a function of x. In this case, the chain rule says that du is du dx times dx. We can integrate both sides. And after composing with a function f of u, then one obtains what is typically called the u-substitution formula. Namely, the integral of f of u du is the integral of f of u of x times du dx dx. Now, of course, this u-substitution formula is just the chain rule in reverse. However, it's very useful if you can determine what is u and what is f. Your goal is the integral on the left, the f of u du, which is hopefully simpler than what you are given on the right, the more complex-looking integral in terms of x. It's best to see this through a simple example. Consider the integral of e to the sine of x times cosine of x dx. You may or may not be able to see what the antiderivative is. However, if we let u be equal to sine of x, then du is cosine of x dx. We can see that e to the sine x is really just the exponential of u, whereas the cosine of x dx is the du term. Thus, by substitution, we can say that this integral is the same as the integral of e to the u du. Now, of course, we all know that the integral of e to the u is simply e to the u plus a constant. We're not quite done in that we need to substitute back in for a function of x. So our original integral evaluates to e to the sine of x plus a constant. Now, we could and should check that this is actually the correct answer. We should differentiate e to the sine of x and see that we obtain e to the sine of x times cosine of x dx. That's the wonderful thing about these types of problems. You can always check your results. Now, in this case, choosing the u and choosing the f were easy, almost transparent. This is not always the case. A trickier sort of example would be something like the integral of x times the square root of x minus 1 dx. In this case, what is the u here? What is f of u? In general, it's best to make a substitution that simplifies your integrand to whatever extent possible. In this case, if we were to let u be equal to x minus 1, It would seem to be trivial since du equals dx. However, notice what happens. X is u plus 1, and square root of x minus 1 is square root of u. We can therefore expand this integrand out as u to the 3/2 plus u to the 1/2. Notice we could not do that with x. Now we can easily integrate this to yield 2/5 u to the 5/2 plus 2/3 u to the 3/2. Substituting back in x minus 1 for u yields the answer 2/5 quantity x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus a constant. I'll leave it to you to check this. Another example that is perhaps not so obvious is the following: the integral of cosecant theta times cotangent theta d theta. Again, in the absence of something obvious to do, try simplifying your integrand. In this case, using the definition of cosecant and cotangent yields cosine theta over sine squared theta d theta. And now it's a bit more apparent which substitution to try. Let's try u equals sine theta. In this case, du is cosine theta d theta, and we see the du sitting right in front of us. This becomes the integral of 1 over u squared times du. That we can certainly integrate to yield negative 1 over u plus a constant. Substituting back in, we get negative 1 over sine theta. That is negative cosecant theta plus a constant. I'll leave it to you to check. We're going to put these techniques to use in a differential equation that models the growth of a tumor. The Gompertz model for the size, n of t, of a tumor as a function of time, t, is the following differential equation: dn dt equals negative a times n times log of quantity b times n. Here a is a constant that is positive, and b is a constant that is between 0 and 1. Using the method of separation, we move all of the n's to the left-hand side, and we obtain dn over n times log of b times n. On the right-hand side, we're left with negative a dt. Now we need to integrate both sides of this equation. How do we perform the integral on the left? We're going to have to do a substitution. If we let u be log of b times n, then du is equal to dn over n. And we see that this integral is going to simplify dramatically to du over u. On the right-hand side, we again have the integral of negative a dt. Computing both the integrals gives us log of u equals negative at plus a constant. As with other equations we've done, we're going to exponentiate both sides to obtain an answer. U is constant e to the negative at. But we're not quite done, because u is not what we were looking for. We were looking for n. And so we must substitute back in for u. Log of b times n is constant e to the negative at. Now, to solve for n, we're going to have to exponentiate both sides again. Doing so, and dividing by b, gives us n, the size of the tumor, as a function of time t, is 1 over b times e to the constant times e to the negative at. This is a double exponential. It has an exponential in the exponent. Now, what about this constant c? I'll leave it to you to check that c is given as the log of b times n naught, where n naught is the size of the tumor at time 0. But deriving the solution is not the end of the story. We'd like to know something about how that solution behaves. Let's consider things from the point of view of equilibria. If we set dn dt equal to 0, what do we observe? We observe that there is an equilibrium at 0. Plugging in n equals 0 certainly gives dn dt equal to 0, as you can see by taking a limit. And it certainly makes biological sense that if the initial size of the tumor is 0, then no tumor will grow. However, there's another equilibrium at n equals 1 over b. In this case, that log term vanishes. What happens when we plot various solutions, n as a function of t? We see that the solution with a non-zero initial condition will converge to this 1 over b equilibrium. This is sometimes called the carrying capacity of the model. Now, indeed, if we plot n dot versus n, we will see these two equilibria arising, and we will see that 1 over b is a stable equilibrium, whereas 0 is an unstable equilibrium. This is what linearization will give. Now, the global perspective in what we have done in this lesson is all about this U substitution formula, but really, it should go under a different name, and you will learn it later in life under the name of the change of variables formula. What we're really doing is changing from x variables to u variables. And this change of coordinates facilitates integration. It makes it easier. For example, if we look at 2x sine x squared, then converting that over to sine of u makes something that's easily integrated to negative cosine of u, and then we go back to the original x coordinates. That allows us to compute a difficult integral by means of a simple integral in a new coordinate system. And that is the important point. Notice that as well we could run things backwards and obtain derivatives of complicated functions by a change of coordinates. That is what we did when we learned the all-important chain rule. Now, why is this perspective important? When you get to multivariable calculus, you are going to use a more sophisticated change of variables formula to solve some truly difficult integrals. Work now on the simple cases, and when you get to multivariable, you'll be fully prepared.
Substitution, or better yet, a change of variables, is one important method of integration. But it's merely the first in an increasingly intricate sequence of methods. In our next lesson, we'll introduce a second technique, that of integration by parts.